Welcome to the Explainer. So today we're doing something a little different. We're not going to treat biostatistics like some dry, dusty set of math equations. Instead, we're framing it as a high-stakes courtroom. Every time researchers publish a clinical trial, they're essentially presenting a case to the medical community. And as focused learners, our job is to act as the ultimate judge. We have to ruthlessly audit a study's conclusions against ground truth reality to figure out if what they're selling is actual medical truth or just a really good statistical illusion.
I want you to really picture this. Imagine you're a tough, skeptical, clinical lawyer. You're reviewing a trial that claims a brand new drug completely cures a devastating disease. I mean, the data looks absolutely amazing on paper, right? But in the back of your mind, you've got to plant that seed of suspicion. Are these findings just pure noise? Is the cure real, or did the researchers just get incredibly lucky with their specific sample of patients? That right there is the foundational question of literally all clinical research.
To get to the bottom of that, here is our roadmap for the Explainer. First, the 50-50 dilemma. Second, we'll dive into the power matrix. Then, an error discrimination drill. And finally, we will wrap up with the threshold seesaw.
All right, let's jump right into Section 1, the 50-50 dilemma, looking at Type I versus Type 2 errors. So these are literally the two biggest traps in clinical research, and it's wild how perfectly the justice analogy maps onto biostatistics here. On one side, we have a Type 1 error, or alpha. That's a false positive. You're basically stating a difference exists when, well, it actually doesn't. In our courtroom analogy, that is the exact equivalent of convicting an innocent person. Now, on the flip side, we have a Type 2 error, or beta. This is a false negative. You state there's no difference, but a true difference actually does exist out there in reality. That's like letting a guilty person go totally free just because you didn't have enough evidence.
Which brings us to a really crucial question. What level of risk are we actually comfortable with? In medical research, the acceptable threshold for a Type 1 error, convicting that innocent person, is known as alpha. And it's typically set at a pretty stark 5%, or 0.05. Essentially, we're saying we are only willing to accept a 5% chance that a study's positive conclusion is just a complete false positive fluke.
Now, contrast that alpha threshold with our beta threshold. The threshold for a Type 2 error, missing a true effect, letting the guilty walk, is generally set quite a bit higher. Typically, it sits at 20%, or 0.20. Why? Well, historically, the scientific community has basically decided that falsely adopting a totally useless drug is far more dangerous than accidentally missing a helpful one.
Okay, before we move on, we have got to clear up a super common, kind of dumb mistake. Please, whatever you do, do not conflate your alpha with your p-value. This happens all the time. Notice the crucial difference here. Alpha is your preset goalpost. It's the absolute threshold of acceptable error you decide on before the trial even begins. The p-value, on the other hand, is the actual score calculated from the observed data after the trial is totally over. If your p-value crosses that alpha goalpost, boom, your result is statistically significant.
Moving right along to Section 2, the power matrix, and how we actually detect the truth. So now, we're shifting our diagnostic dividing line from just missing a difference to the actual probability of finding one. Power, which is mathematically expressed as 1 minus beta, is the probability of correctly rejecting the null hypothesis when it is in fact false. In plain English, it's the true positive rate. Honestly, I like to think of power as a giant mathematical net that we cast out into this massive ocean of clinical data. If there's a true difference out there, like a real fish to catch, power is the probability that our net is actually big enough and strong enough to catch it. But how do we actually build a bigger net? Well, there are 4 interlocking variables that drive this power matrix: sample size, effect size, variance, and the alpha level. And here's the kicker. These 4 variables are totally linked. If you pull one lever, it automatically shifts the others, which completely changes your study's ability to detect the truth.
Let's actually walk through this matrix row by row. First, if you increase the sample size, you naturally narrow those distribution curves, which drastically increases your power. Second, if you have a massive effect size, say a drug that cures 80% of people versus just 2%, well, that huge difference is obviously much easier to detect, right? So that boosts power. Third, if you lower the variance, you're essentially reducing the background statistical noise, which again increases power. And finally, if you increase alpha, making it artificially easier to claim a victory, you do increase your power. But, and this is a big but, you take on way more risk of a false positive.
Which brings us to another classic dumb mistake you've got to watch out for. Imagine a trial with only 15 patients per group, and it finds no statistically significant difference. Amateurs will look at that and immediately conclude the drug is completely useless. But as you know now, the study was probably just underpowered. The real signal might absolutely exist, but casting a tiny, flimsy net into a massive ocean means you're almost guaranteed to commit a type 2 beta error.
All right, time to test this out. Section 3, the error discrimination drill. Let's look at some real-world scenarios.
Okay, here is scenario A. A trial finishes with a p-value of 0.12 and firmly concludes a new antiarrhythmic agent has absolutely no effect on mortality. However, fast forward 2 years later, and a massive registry of 50,000 patients reveals it actually does reduce mortality by 4%. So put on your clinical lawyer hat right now. Which error was committed in that very first trial?
And the verdict is in. That was a type 2 error, a beta error. The original trial completely failed to find a true difference that actually existed in the real world. Why? Well, because the difference was relatively small, only 4%, and the original trial just lacked sufficient power. It most likely had an inadequate sample size, so it couldn't separate that true signal from the background noise. They let the guilty guy go free.
Let's jump right into scenario B. A small startup runs a fast-track trial on an Alzheimer's drug in just 40 patients. They proudly report a statistically significant improvement with a p-value of 0.04. Investors absolutely go wild. But later, a massive phase 3 trial in 3,000 patients shows absolutely zero clinical benefit. So evaluate this startup's data for a second. Which error was committed here?
The verdict here is a type 1 error, an alpha error. The initial positive result in those 40 patients, it was just a pure statistical fluke, a total false positive. By sheer random chance, the patients in the treatment arm happened to improve. This is your classic convicting an innocent person error. And man, it highlights exactly why we demand large phase 3 trials to verify early, noisy data.
Finally, Section 4, the threshold seesaw, looking at the delicate balance between alpha and beta.
This brings us to our final executional pearl, predicting exactly how alpha and beta move when we manually change the rules of the game. Now, assuming you hold your sample size completely constant, alpha and beta literally exist on a seesaw. They move in exact opposite directions. If you lower your alpha threshold from 0.05 down to 0.01, making it incredibly hard to claim a victory, your type 1 error drops, sure, but your type 2 error goes up, causing your overall power to drop. Conversely, if you raise your alpha from 0.01 up to 0.05, your risk of a false positive type 1 error increases, but your type 2 error decreases, which mathematically boosts your power. You simply cannot change one without impacting the other. It's a total trade-off.
Which brings us to the ultimate question you really have to ask yourself every single time you read a clinical study. Because we can never achieve perfect certainty, biased statistics kind of forces us to choose our poison. So, in the pursuit of medical truth, which error are we actually willing to live with? Falsely adopting a useless intervention or completely missing a life-saving cure? Keep that question in the back of your mind the next time you review a trial, and I promise you, you'll never look at the data the same way again. Thanks for joining me on this explainer, and keep learning.